The night sky holds a secret deeper than any star. For all of human history, we have looked up and seen not just points of light, but patterns, rhythms, a silent architecture governing everything. Where did that cosmic order come from? This is the single most profound question we can ask about reality itself. In this exploration, we will journey through 30 mind-expanding theories, from the spiritual convictions of ancient cultures to the bleeding edge of theoretical physics, each one a different answer to that ultimate mystery. By the end, you will see the universe not as a random collection of stuff, but as a puzzle with competing, breathtaking solutions. We will examine if our entire existence is a mathematical structure, a sophisticated simulation, or the outcome of an endless cosmic evolution. What one idea, when you really consider it, feels like it could be true? That instinct to find a pattern in the chaos is perhaps our oldest scientific impulse. For thousands of years, the most brilliant minds across every civilization were not just stargazers, they were cosmic detectives. They watched the sun march across the sky with unwavering consistency. They tracked the moon through its phases, and they saw planets that moved against the backdrop of stars in strange, looping dances. The question wasn't just what these lights were, but why they moved with such intricate, predictable grace. This was the birth of cosmology, a quest that has always been part science and part philosophy. In ancient Greece, thinkers like Ptolemy constructed an astonishingly complex model of crystal spheres, placing Earth firmly at the center of a celestial clockwork. His system was wrong, but its goal was profound, to mathematically describe the observed order. Centuries later, Isaac Newton saw a different kind of pattern, not in spinning spheres but in an invisible force. An apple falls, the moon orbits, and he realized it was the same phenomenon, a universal law of gravity that could be written as a simple equation. This was a monumental leap, the idea that the cosmos operates by consistent, knowable rules. Each of these historical steps, from myth to mathematics, was a piece of the same puzzle, a slow assembling of the question we now ask with such precision. Why is the universe not a formless, eternal noise? Why does it have laws at all? This long, human struggle to map the heavens, from clay tablets to supercomputers, is the essential backdrop. It shows us that our modern theories, no matter how strange they sound, are not wild guesses. They are the latest chapters in an epic story of observation and reason, the natural next step in a conversation that began when the first person looked up and wondered. These competing answers to our cosmic question can feel overwhelming, like a library with no organizing system. To make sense of it all, we can sort these 30 mind-expanding ideas into 4 broad shelves. First, metaphysical theories. These are the oldest and often the most profound, rooted in philosophy, spirituality, or the concept of a divine mind. Here, cosmic order is not an accident but a conscious intention, a purpose woven into the fabric of existence from the very beginning. Second, physical theories. This is the realm of science as we know it, where order emerges from fundamental laws and particles, from the Big Bang to quantum fields. The universe runs on a code we are slowly deciphering. Third, mathematical theories. For some thinkers, the laws of physics are just a shadow of a deeper truth, that reality is ultimately a structure of pure logic and numbers. In this view, mathematics doesn't just describe the universe, it is the universe. And fourth, emergent theories. Here, grand cosmic order isn't written in from the start. Instead, it bubbles up from below, an inevitable product of simple components following simple rules, self-organizing over immense spans of time and space. These categories are not rigid boxes. Many of our most fascinating theories will blur the lines, borrowing from philosophy to inform physics, or using mathematics to explain emergence. But this framework gives us a map for the journey ahead, a way to see how humanity's deepest questions about meaning and its most rigorous tools of discovery are all converging on the same magnificent mystery. With this map in hand, we begin where humanity itself began, not with equations but with awe. The first shelf on our map, the metaphysical, holds theories that begin not with particles but with purpose. Among them, the divine blueprint is perhaps the most ancient and enduring explanation for cosmic order. Across countless cultures and millennia, a common thread emerges, the idea that the intricate harmony of the heavens reflects the mind of a creator. From the rhythmic cycles described in Vedic texts to the concept of a divine logos in ancient Greek philosophy, the universe was often seen as a deliberate work of art, its laws the brushstrokes of a supreme intelligence. This perspective asks us to consider the very nature of a law itself. Is a law of physics something that simply exists, or is it more like a rule, a decree set down by a governing authority? The modern version of this idea often points to the phenomenon of fine-tuning. Scientists have discovered that the fundamental constants of our universe, like the strength of gravity or the mass of an electron, appear to be exquisitely balanced. If any one of these numbers were even slightly different, stars would not form, chemistry would be impossible, and life could never arise. To some, this breathtaking precision feels less like a lucky roll of cosmic dice and more like the signature of a designer, evidence that our universe was intentionally calibrated for complexity. This theory, of course, sits at the heart of a long and nuanced dialogue between scientific and spiritual worldviews. It is less a scientific hypothesis to be tested and more a philosophical stance on the origin of existence itself. It challenges us with a fundamental question: does profound order necessarily imply a conscious order giver? Or can such magnificent structure arise from purely natural, unconscious processes? The power of the divine blueprint theory is that it provides a deeply satisfying answer to the why, anchoring cosmic law in meaning and intention. As we move forward, we will see how every other theory, in its own way, is an attempt to answer that same profound why, but without invoking a designer. The journey from this point onward is essentially a search for alternative sources of that breathtaking cosmic harmony we all observe. But if the cosmos is not a divine creation, what is its ultimate substance? One radical answer comes from physicist Max Tegmark, who proposes the mathematical universe hypothesis. This idea pushes past the notion that mathematics is merely a useful tool, a language we invented to describe the world. Instead, Tegmark suggests something far more profound, that our physical reality isn't just described by mathematics, it is mathematics. Think of it this way: we don't say a circle is described by the equation x squared plus y squared equals r squared. The equation is the circle in its purest, most abstract form. In this view, our universe with its galaxies, planets, and people is not the primary reality. It is a shadow, a physical manifestation of an underlying, immutable mathematical structure. The so-called laws of physics, then, are not rules that the universe follows. They are simply the inherent, logical properties of that structure, in the same way that the angles of a triangle always add up to 180 degrees. This turns our understanding inside out. An electron isn't a tiny ball of matter that happens to have certain mathematical properties like charge and spin. The electron is that specific bundle of mathematical relations. Its existence and behavior are dictated by the logic of the structure it inhabits. This leads to a fascinating and almost philosophical question, one that has divided thinkers for centuries. Is mathematics discovered or invented? Do we uncover eternal truths, like archaeologists brushing dust off a hidden tablet? or do we construct a useful fiction like architects drafting a blueprint? The mathematical universe hypothesis strongly favors discovery. It posits that mathematical truths exist independently in a kind of abstract realm, and our universe is one particular structure that has somehow been instantiated into physical reality. It is a breathtakingly elegant idea, solving the puzzle of cosmic order by making it a logical necessity. If the universe is math, then of course it is orderly, just as 2 plus 2 must always equal 4. This theory dissolves the boundary between the concrete and the abstract, suggesting that at the deepest level, existence is not made of stuff, but of information, of relationships, of pure thought. Yet if the universe is a mathematical structure, how did that structure become our physical, expanding reality? To answer that, we must travel back to the very beginning, to a theory that provides our most robust scientific origin story for cosmic order, cosmic inflation, and symmetry breaking. Picture the universe not even a second old, a seething, unimaginably hot and dense soup where all the fundamental forces of nature are merged into one unified superforce. In this state, perfect symmetry reigns, but it is an unstable, fiery symmetry. Then, something extraordinary happens. In a fraction of a second, a field of energy inherent to space itself triggers a runaway expansion, inflating the universe faster than the speed of light. This is not expansion into space, but the rapid stretching of space itself. This inflationary epoch did two crucial things that created the large-scale order we see. First, it took any tiny irregularities and stretched them to cosmic proportions, effectively ironing the universe flat and smooth, which is exactly what our telescopes observe in the uniform glow of the cosmic microwave background, the afterglow of the Big Bang. Second, and more subtly, as the universe cooled during this rapid expansion, that perfect symmetry began to crack. Think of it like water freezing into ice. In its liquid state, water looks the same in every direction, it's symmetric. But when it freezes, it forms a crystal with a specific, rigid structure. The symmetry is broken, but a new, more complex order emerges. In the early universe, as it cooled, the unified force broke apart or crystallized into the distinct forces we know today: gravity, electromagnetism, and the nuclear forces. Each break established a new set of rules, a new law for that force to follow. This is the profound insight. The laws of physics as we know them were not written in stone from eternity. They froze into place during a specific, transformative event. The cosmic order governing galaxies and atoms is not a timeless decree, but a relic of a broken symmetry, a cosmic phase change that turned primordial chaos into a universe with rules. This theory, supported by detailed observations of the sky's faint microwave whisper, shows us that order can be a physical outcome, an inevitable product of cooling and expansion from a hot, dense beginning. It moves the mystery of cosmic law from the realm of pure philosophy into the domain of testable cosmic history, suggesting that even the most fundamental rules of reality have a birthday. But a broken symmetry that births physical law leads to another deeply personal question. Why do those specific laws seem so perfectly tailored for us? This brings us to the fourth mind-expanding idea, the Anthropic Principle. At its heart, this principle is a statement about observation. The weak version is almost a tautology. We can only find ourselves living in a universe capable of supporting life. We are, in a sense, cosmic survivors. We are not observing the universe from some neutral, outside position. We are a product of its conditions. If the constants of nature were different, stars and planets and complex chemistry might never have formed, and there would be no one here to wonder about it. The strong version of the principle goes a step further, suggesting the universe must, in some fundamental way, have properties that allow conscious observers to arise within it. This is where the idea becomes controversial, as it edges into philosophical territory about purpose. The Anthropic Principle does not explain how the universe got its fine-tuned constants, but it offers a powerful lens for why we perceive them as fine-tuned. It shifts the question from why is the universe so hospitable to life, to why are we in the part of reality that is hospitable. One compelling answer emerges from the realm of cosmology itself, the multiverse. Imagine not one universe born from inflation, but a vast, perhaps infinite, ensemble of them, a cosmic landscape where every possible set of physical laws and constants is realized somewhere. In most of these universes, the numbers are wrong, atoms are unstable, gravity crushes everything instantly, and no complexity emerges. But in a tiny, improbable fraction, the dice land just right. We inevitably exist in one of those rare Goldilocks pockets. Our amazement at the perfect balance is not evidence of design, but simply a consequence of our own existence. We are the winners of a cosmic lottery so vast that even the most unlikely outcomes are guaranteed to happen somewhere. This perspective reframes fine-tuning from a miraculous accident into a statistical inevitability across a grander canvas of reality. It is a humbling thought that the very laws we study with such reverence might be local bylaws, just one set of rules in an infinite cosmic library where every possible book of physics is written. The Anthropic Principle, especially when paired with the multiverse, asks us to consider our place not just in space, but in a much broader landscape of possibility, where our existence becomes the one fixed point from which we must reason about everything else. Plato's vision of reality offers a stark and beautiful alternative to the multiverse. 2,500 years ago, this Greek philosopher proposed that the world we see and touch is merely a shadow, a flickering image cast on a cave wall. True reality, he argued, exists in a transcendent dimension he called the world of forms. This is a realm not of matter, but of perfect, eternal blueprints, the ideal essence of everything, from justice and beauty to the very shape of a circle or a triangle. In this metaphysical framework, cosmic order finds its ultimate source. The reason planets move in such graceful, elliptical paths is not because of gravitational equations, but because they are imperfectly participating in the perfect, timeless form of the circle or the sphere. The laws of physics themselves would be echoes of these pure, abstract ideals, casting their rational light onto the messy, changing world of substance. Plato's theory directly challenges the notion that order emerges from particles or energy. Instead, order is imposed from above, or rather from beyond, by principles that exist independently of the universe they govern. This idea has echoed through the centuries, profoundly influencing theology, philosophy, and even the foundations of mathematics. When a mathematician proves a theorem about triangles, is she discovering a truth about an abstract, perfect form that exists outside of any drawn line, or is she merely manipulating human-made rules? Plato would argue for the former, that she is brushing against a reality more fundamental than atoms. This perspective creates a fascinating tension with modern science, which builds knowledge from the ground up, from observation and experiment. Plato's approach is top-down, beginning with the perfect idea and seeing the physical world as its flawed reflection. It asks a haunting question that still resonates. Is the breathtaking mathematical harmony we find in nature a clue that we are touching something eternal, a realm of pure reason that gives shape and meaning to our transient existence? While we may not find the world of forms in a telescope, its philosophical shadow stretches across our search for cosmic order, reminding us that the source of law could be as much about ideal truth as it is about physical cause. But if Plato's world of forms feels abstract, our next theory proposes a reality even more illusory. The holographic principle suggests that everything we perceive, from the furthest galaxy to the feeling of your own hand, might be a projection. This astonishing idea didn't come from philosophy, but from the most extreme objects in the cosmos, black holes. In the 1970s, physicist Jacob Bekenstein made a startling calculation. He found that the maximum amount of information, the total number of yes or no answers needed to describe everything inside a black hole, is not proportional to its volume as you might expect. Instead, it is proportional to the surface area of its event horizon, the point of no return. It was as if all the data for a three-dimensional object could be perfectly stored on a two-dimensional surface. Years later, Leonard Susskind and others expanded this into a full-blown principle for the universe itself. They proposed that all the information contained within any volume of space, every particle, every force, can be completely encoded on the boundary that surrounds it, like the data on a holographic film. In a hologram, a flat, two-dimensional surface, when illuminated with a laser, creates a stunningly realistic three-dimensional image that you can walk around. The holographic principle asks us to consider that our entire universe might work the same way. The three-dimensional reality we move through, with its depth and solidity, could be a magnificent illusion projected from a vast, two-dimensional surface at the edge of the cosmos. This turns our intuition about reality inside out. In this view, the fundamental ingredients of the cosmos are not particles or strings, but bits of information, like the ones and zeros on a cosmic hard drive. The laws of physics we spend centuries trying to uncover, from gravity to quantum mechanics, would not be the bedrock rules. They would be emergent phenomena, like the rules of grammar that emerge from the flow of language, or the laws of thermodynamics that emerge from the chaotic dance of countless molecules. They are the consistent patterns that arise when an immense amount of two-dimensional data is projected into the three-dimensional theater of our experience. It redefines space and time themselves, suggesting they are not primary but secondary, a kind of user interface generated for our benefit. So the cosmic order we seek, the beautiful mathematical symphony of the universe, might be the output of a cosmic processor, the result of an unimaginably vast calculation happening on a distant, flat screen we can never see. It is a theory that merges the physics of the very large with the physics of the very small, hinting that at the deepest level, reality might be made of nothing more substantial than pure information, written on the skin of the world. If reality is a holographic projection, could it also be a deliberate construction? This question leads us to a theory that has leapt from science fiction into serious philosophical debate, the simulation hypothesis. Popularized by philosopher Nick Bostrom, this idea suggests our entire universe, with all its galaxies, history, and conscious experience, is not base reality. It is an incredibly sophisticated simulation, akin to a hyper-advanced video game, running on the hardware of a civilization far more technologically mature than our own. In this view, the cosmic order we are trying to decode, the laws of physics, are not fundamental truths of nature. They are simply the programmed rules of the simulation, the underlying code that governs how the virtual environment behaves, much like the laws of gravity or collision in a computer game are lines of software. This theory, while highly speculative, gains a strange kind of traction when we look at our own technological trajectory. Our computing power grows exponentially. We create increasingly immersive virtual worlds, and we are beginning to model complex systems, even simple universes, in silico. If this trend continues for thousands or millions of years, a post-human civilization might possess the capacity to run vast, conscious simulations, perhaps even billions of them. From a statistical standpoint, if that's true, then the number of simulated minds would vastly outnumber the minds in the original, base reality. Therefore, the odds are we are more likely to be one of those simulated beings than an organic one in the original world. This line of reasoning forces profound philosophical questions. What is consciousness if it can be rendered in a simulation? Could we ever know if we are inside one? More unsettling for the scientist, if the simulation hypothesis were true, the entire quest for a theory of everything, for the ultimate laws of physics, might be a fascinating but ultimately futile exercise. We would be like characters in a game trying to reverse engineer the game engine's source code, only to discover the rules are arbitrary, designed for efficiency or aesthetics by the programmers. The constants of nature would be parameters they could tweak, not deep truths. This notion connects powerfully to concepts in digital physics, which we will explore soon, where the universe is seen as a computational process. The simulation argument doesn't offer a scientific test, but it serves as a powerful thought experiment, a mirror held up to our assumptions about reality. It asks us to consider that the most elegant explanation for cosmic order might not be a divine mind or a mathematical structure, but a line of code written by beings whose motives we cannot even begin to fathom. The simulation argument suggests our laws could be arbitrary code, but what if they are simply one possible setting in a cosmic factory of realities? This brings us to the eighth mind-expanding theory, eternal inflation and the multiverse. We already saw how a brief period of inflation could smooth and shape our single universe, but eternal inflation takes that concept and runs with it into infinity. Imagine the energy field that drove that initial expansion doesn't just switch off everywhere. Instead, like a pot of water boiling eternally, quantum fluctuations cause new pockets of space to continuously bubble off. Each of these bubbles is a separate universe, inflating within the greater, churning foam of the multiverse. Crucially, when each bubble universe forms, the symmetry breaking that establishes its laws is a random quantum event. This means each bubble gets its own unique set of physical constants, its own version of the laws of physics. In some bubbles, gravity might be 1 billion times stronger, instantly collapsing everything into black holes. In others, the nuclear forces might be too weak to bind atoms together, leaving only a thin haze of particles. Our universe, with its just right balance for stars, planets, and life, is simply one of these countless bubbles, a rare but statistically inevitable oasis of stability in an endless desert of inhospitable realities. This theory provides a powerful, naturalistic answer to the puzzle of fine-tuning. We don't need to ask why our universe is so perfectly calibrated, because in an infinite multiverse, every possible calibration occurs somewhere. We just happen to live in one where the numbers allow us to exist and ask the question. Cosmic order, then, is not a universal principle. It is a local phenomenon, a set of bylaws specific to our cosmic neighborhood. What we perceive as fundamental and immutable might be nothing more than a random roll of the quantum dice frozen into place at our bubble's birth. This perspective is both humbling and expansive. It suggests that the ultimate reality is not a single, ordered cosmos, but a chaotic, frothing ensemble where order is the rare exception, not the rule. It shifts our search from finding the one true source of law to understanding why our particular pocket of chaos settled into such beautiful, predictable harmony. The multiverse doesn't diminish the wonder of our universe's order. It simply places that wonder against a backdrop of infinite possibility, where our existence becomes a fascinating data point in a much larger and far stranger story. Einstein's theory of relativity offers a vision of cosmic order so complete it borders on the absolute. In this framework, time is not a flowing river carrying us from past to future. Instead, it is a dimension, much like the 3 dimensions of space, woven together into a single, unchanging fabric called spacetime. This leads to the concept of the block universe, a static 4-dimensional structure where every moment, from the Big Bang to the farthest future, exists simultaneously. Think of it not as a movie playing frame by frame, but as the entire film strip laid out at once, with every scene fixed in its place. In this view, cosmic order is not a set of rules that events obey over time. It is the total, immutable geometry of the block itself. The path of every planet, the life of every star, and every choice ever made is not unfolding, but simply is, a permanent feature of the cosmic landscape. This introduces a profound and challenging idea, determinism. If the block is fixed, then every event is the inevitable consequence of the initial conditions at the beginning of the universe, playing out with the precision of a mathematical equation. The feeling of making a free choice in this model is an illusion, a story our consciousness tells itself as it moves along a predetermined track through the block. The universe's entire history is one vast, ordered tapestry with no loose threads. This perspective can feel deeply unsettling, as it seems to remove agency and chance from reality. Yet, it also presents a cosmos of breathtaking and absolute order, where what we perceive as chaos is merely a limitation of our perspective, our inability to see the entire woven pattern at once. The deterministic block universe represents perhaps the ultimate expression of a clockwork cosmos, a vision where the source of order is the very frozen structure of space-time itself. However, this beautifully ordered picture runs into a formidable challenge from the quantum realm, where probability and uncertainty seem to be fundamental features, not illusions. This tension between Einstein's serene, deterministic block and the fuzzy, probabilistic quantum world sits at the heart of modern physics, forcing us to ask if true cosmic order allows for genuine randomness, or if even quantum dice are loaded in ways we do not yet understand. But the serene certainty of the block universe shatters upon contact with the quantum world. Quantum indeterminacy introduces a fundamental dice roll at the heart of reality. At the microscopic scale, particles do not have definite properties until they are measured. They exist in a haze of probabilities called a superposition, a state where all possible outcomes coexist. This is not a limitation of our knowledge, it is a feature of the universe itself, an inherent randomness woven into the fabric of existence. So how does the crisp, predictable order of our everyday world, where apples fall and planets orbit, emerge from such foundational chaos? The answer lies in a process called decoherence. Imagine a single, isolated electron spinning in two directions at once. Now, imagine that electron interacts with just a single photon of light. That photon carries away information about the electron's state, and in doing so, it entangles with the electron. Now scale this up astronomically. In our warm, bustling world, every particle is constantly bombarded by trillions of other particles and forces. Each interaction is a tiny leak of information into the environment, an irreversible entanglement with the wider universe. This relentless process, decoherence, effectively forces quantum possibilities to choose, collapsing the haze of probabilities into the single, definite state we actually observe. It is as if the universe is taking a blurry quantum photograph, and the act of developing it through countless interactions produces a sharp, classical image. This suggests a radical view of cosmic order. The laws governing planets and galaxies are not pre-written in a deterministic script. They are statistical habits that emerge when enough quantum dice are thrown. They are the reliable patterns that surface from an ocean of underlying randomness, much like the predictable pressure of a gas emerges from the chaotic dance of countless molecules. This reveals a universe where order and chance are not opposites but partners. The grand cosmic architecture we marvel at is not a rigid, frozen structure. It is a dynamic, probabilistic process, a kind of stability that emerges from flux over immense spans of time. It challenges us to see regularity not as a divine decree or a mathematical absolute, but as the most likely outcome in a game where the dice are always rolling, a breathtaking balance between chance and necessity that we will see echoed in the dance of complex systems. This inherent connection between mind and cosmos finds its boldest expression in a theory that moves from the laboratory to the realm of belief. the law of attraction proposes that cosmic order is not a distant, impersonal force, but a direct reflection of consciousness itself. In this view, our thoughts, beliefs, and focused intentions are not just private events inside our skulls. They are active forces that shape the fabric of reality through a universal principle of like attracting like. It is a vision where the individual mind and the cosmic mind are deeply intertwined, where order does not exist independently out there, but is constantly being manifested from within through collective or individual focus. While this idea exists firmly outside the boundaries of conventional scientific validation, its enduring appeal is profound. It speaks to a deep human intuition that we are not passive observers in a predetermined universe, but active participants in its unfolding. It bridges the vast gap between psychology and cosmology, suggesting that our inner emotional and mental states might resonate with and even influence the outer structure of reality. This perspective flips the scientific quest on its head. Our relentless search to decode cosmic order, from ancient star charts to quantum equations, might itself be a creative act. By looking for patterns, by believing in a rational, comprehensible universe, are we not, in a sense, using the power of our attention to call that very order into being? It invites a reflective, almost meta, question about our place in the cosmos. How much of the beautiful mathematical harmony we discover is an objective feature of an external world, and how much is a projection of our own deeply ingrained need for meaning and predictability? The theory of conscious creation does not offer testable predictions about galaxy formation, but it offers a powerful narrative about agency. It suggests that the source of cosmic order might not be found in a singularity or a multiverse, but in the very act of observation and expectation, placing the human mind not at the end of a long causal chain, but at the very center of the creative process. The line between a living planet and a sterile one may be far thinner than we think. If consciousness can be seen as a creative force, then life itself might be an ordering principle on a cosmic scale. This is the profound leap of the Gaia hypothesis, extended far beyond our blue marble. Originally proposed by scientist James Lovelock, Gaia suggests Earth functions not just as a rock with life on it, but as a single, self-regulating superorganism. Its oceans, atmosphere, and biosphere are linked in intricate feedback loops that maintain conditions suitable for life over billions of years, like a planetary thermostat. Now stretch that vision across the galaxy. This expanded theory posits that life and cosmic order are not separate phenomena, where life merely inhabits a pre-ordered universe. Instead, they are deeply intertwined in a co-creative dance. It speculates that the universe possesses an inherent biophilia, a tendency to favor and foster the conditions for life, not by divine plan, but through the complex chemistry of planets and stars. In this view, biological processes might subtly influence planetary and even stellar systems. Imagine a planet where early microbial life releases certain gases that stabilize its climate, allowing more complex life to evolve, which in turn alters the reflectivity of the continents, further regulating temperature. This is a local feedback loop. On a grander, more speculative scale, could the collective activity of life in a galaxy over eons influence the distribution of elements or the very dust between stars? Could a living planet's biosphere affect its magnetic field or atmospheric composition in ways that send faint, detectable signals across the light years? This idea connects ecology to cosmology in a breathtaking way. It proposes that cosmic order is not just a story of physics and math, but also of biology. Order emerges not only from the cooling of plasma or the breaking of symmetries, but from the complex, persistent struggle of living systems to create and maintain stable niches for themselves. The harmony we seek might be, in part, a biological harmony, a symphony played by countless organisms interacting with their environments, slowly tuning their worlds into places where life can persist and flourish. While highly speculative and difficult to test, this theory offers a radically different narrative. It suggests we are not accidental guests in a mechanical universe. We and any life out there might be active participants in shaping cosmic order, weaving biological complexity into the very fabric of space and time, one stable, living world at a time. But if life is a fleeting expression of cosmic order, what happens when the universe itself reaches its end? Our linear story of a Big Bang followed by expansion faces a profound alternative, the cyclic model and the idea of eternal return. This theory, championed by thinkers like physicist Roger Penrose, offers a breathtakingly different vision. Instead of a single, one-way journey from a fiery beginning to a cold, dark end, the cosmos undergoes an endless, rhythmic dance of death and rebirth. In Penrose's conformal cyclic cosmology, our current expanding universe, or eon, will eventually stretch into an unimaginably vast, cold, and empty state. But in this extreme thinness, a remarkable transformation occurs. As all matter decays and distances become meaningless, the universe forgets its scale. It becomes smooth and featureless, mathematically identical to the hot, dense singularity of a new Big Bang. From this seamless transition, a new eon ignites, inheriting a subtle imprint of order from the universe that came before. In this model, cosmic order is not created once. It is eternal and self-renewing, passed like a cosmic baton from one cycle to the next. The laws of physics we are trying to decode are not the bylaws of a single universe, but the timeless, unchanging rules of an infinite sequence. This avoids the philosophically troubling concept of a singular beginning, a moment before which nothing existed. Instead, time itself becomes cyclic, with no true start or finish, only an endless loop of cosmic seasons. This offers a deeply poetic vision of order as an endless dance, a universe that breathes in and out across eons far longer than our own. It contrasts sharply with our standard linear narrative, suggesting that every galaxy, every star, and every civilization that ever could exist might have done so before and might do so again in some form in a future cycle. It invites us to contemplate infinity not as a void, but as a recurring melody, where the source of cosmic harmony is simply the eternal rhythm of existence itself, forever renewing its own majestic, ordered patterns. The eternal return of cyclic cosmology offers a grand vision of order, but for the physicist working today, the quest is far more focused, a search for a single, unifying key. This is the dream of a theory of everything, the idea that all the fundamental forces of nature, gravity, electromagnetism, and the nuclear forces, are not separate phenomena at all. They are different facets of one underlying, elegant principle, waiting to be described by a single master equation. In this view, cosmic order is not a collection of disparate rules, but the direct manifestation of this ultimate theory. The breathtaking diversity we see, from the swirling of galaxies to the bonds of a molecule, would all arise from one simple, profound source. It is the belief that the universe's apparent complexity is a magnificent mask hiding a deep and ordered simplicity. The current front-runners in this century-long pursuit are frameworks like string theory and loop quantum gravity, each taking a radically different approach to unification. String theory proposes that the most basic constituents of reality are not point-like particles, but unimaginably tiny, vibrating strings. The different notes of this cosmic symphony, the various frequencies and modes of vibration, would produce all the particles and forces we observe. Gravity, in this picture, is just another vibration, finally brought into the quantum family. Loop quantum gravity, on the other hand, suggests that space itself is not smooth and continuous, but woven from a fabric of tiny, discrete loops, a kind of quantum tapestry. Here, gravity emerges naturally from the geometry of this woven space. While these theories remain mathematically complex and experimentally elusive, the very pursuit reveals something profound about our understanding of cosmic order. It reflects a deep-seated conviction that the universe is, at its heart, unified and logical. The drive to find one equation to rule them all is not just scientific ambition. It is a philosophical stance, a belief that the source of all law is singular and elegant. This quest is the engine of modern physics, and its promise is staggering that if we ever find this theory, it would not just describe the universe, it would reveal the true, singular origin of all cosmic laws and the very structures they govern. John Wheeler's mind-bending idea pushes the Anthropic Principle into a far more active role. He called it the Participatory Anthropic Principle, and it begins with a simple, profound question. Why does the universe appear so orderly and mathematical to us? Wheeler's radical answer is that it becomes that way through our act of looking. In the strange world of quantum mechanics, a particle does not have a definite position or state until it is measured. Before observation, it exists as a cloud of probabilities. Wheeler extended this quantum weirdness to the cosmos itself. He proposed that the universe, in its earliest moments, existed in a fuzzy, undefined state of pure potential, a superposition of every possible history and set of physical laws. Then, much later, when the first conscious observers evolved, creatures capable of asking questions and making measurements, their act of looking back in time, in a sense, solidified one specific history. It selected one thread of reality from the quantum haze. In this view, cosmic order is not a pre-existing script. It is a story that is only written down when it is read. We are not just survivors in a pre-tuned universe. We are the authors, retroactively giving it a definite form and structure through our very existence and our curiosity. This merges physics with philosophy in a dizzying loop. It suggests that the universe needed life, needed observers, to bring itself into full being. The elegant laws we discover are not independent truths we uncover. They are the consistent patterns that emerge from a dialogue between the cosmos and the mind. It transforms us from accidental tourists into essential participants, our consciousness woven into the fabric of reality itself. This idea challenges the bedrock of scientific objectivity, the assumption that a reality exists out there, separate from us. Instead, it paints a picture of a co-creative universe where the quest for understanding is not a passive observation, but the final step in a cosmic process that began 14 billion years ago. The idea that we are participants in a cosmic story leads to a startling question. What if the story itself is being computed? This brings us to the 16th mind-expanding theory, digital physics and cellular automata. Inspired by the rise of computers, this perspective suggests the universe is not a collection of fields or particles in the traditional sense. It is a vast, running computation. In this view, reality is fundamentally digital, composed of discrete bits of information, like the ones and zeros in a computer, following a set of algorithmic rules. Space and time themselves might not be smooth and continuous, but rather a grid, a lattice of tiny, indivisible points, like the pixels on a screen. Cosmic order, then, is not a product of mysterious forces, but the emergent output of a cosmic program running on a substrate we cannot directly perceive. This reframes everything. The laws of physics we have spent centuries uncovering, from gravity to quantum mechanics, would not be fundamental truths of nature. They would be the high-level software, the consistent patterns that emerge from the low-level code processing beneath. It is a modern, technological take on ancient ideas of cosmic design, replacing a divine architect with a cosmic programmer and a grand blueprint with a source code. Thinkers like Stephen Wolfram have explored this idea through the study of cellular automata, which are incredibly simple computational systems. Imagine a grid of squares, each one either black or white. A basic set of rules determines each square's next state based on the colors of its neighbors. From this minimal starting point, running the program can generate astonishingly complex, intricate, and seemingly organic patterns that evolve over time, all from pure logic. This suggests a profound possibility. Our unfathomably rich and ordered cosmos, with its galaxies and life, might not require infinitely complex initial conditions. It could be the magnificent, unexpected output of a relatively simple set of rules iterated over cosmic scales of space and time. The digital universe hypothesis offers a cold but elegant answer to the origin of cosmic order. Harmony and structure are not written in from the beginning. They are computed into existence step by logical step by the relentless processing of reality itself. David Bohm saw the universe not as a collection of separate things but as an undivided whole. This physicist, troubled by the fragmented nature of quantum theory, offered a radical alternative, the implicate order. In this view, the world we experience with its distinct objects and events is merely the explicate order, the unfolded, tangible surface of reality. Beneath it lies a deeper, implicate realm, a kind of cosmic hologram where everything is enfolded into everything else. Here, the entire past, present, and future of the cosmos exist in a state of profound interconnection, a seamless unity. What we perceive as the birth of a star or the fall of a leaf is not an isolated event, but a moment where a tiny aspect of this implicate whole unfolds into our visible reality, only to enfold back again in a continuous process Bohm called the holomovement. This perspective reframes cosmic order entirely. The laws of physics are not external rules imposed on separate particles. They are the consistent patterns of this endless unfolding, the habitual ways in which the implicate whole expresses itself. Quantum phenomena, like the spooky connection of entangled particles that instantly influence each other across vast distances, are not bizarre exceptions in Bohm's view. They are direct glimpses into the implicate order, evidence that at the fundamental level, separation is an illusion. The universe is a single, flowing entity, and what we call order is the relational dance of its parts within the whole. This theory resonates deeply with certain mystical and holistic worldviews, which have long spoken of an underlying unity to all existence. It shifts our search from finding the source of law to understanding the process of manifestation, from a universe built like a machine to a cosmos that breathes, unfolds, and enfolds in an eternal, ordered rhythm of becoming. If the universe is fundamentally mathematical, we must ask where mathematics itself comes from. The answer, for some, lies not in physics but in pure logic. This 18th theory, rooted in the foundations of mathematics, suggests that cosmic order originates from the most basic axioms of set theory, the rules that govern collections of objects. Consider the Zermelo-Fraenkel axioms, often with the addition of the axiom of choice, which form the bedrock of modern mathematics. These are not equations describing nature. They are self-evident statements about existence, membership, and infinity, from which all of mathematics, from simple arithmetic to complex geometry, can be rigorously derived. If our physical reality is indeed a mathematical structure, as Max Tegmark and others propose, then these abstract axioms are not just human inventions for calculation. They become the ultimate source code, the logical constraints that define every possible structure, including the one we happen to inhabit. This perspective places cosmic order in a realm entirely independent of space, time, or matter. It suggests that the laws of physics we observe are not primary. They are secondary consequences of a deeper, logical necessity. The universe behaves the way it does because any coherent, self-consistent mathematical structure must obey the foundational rules of logic and set theory. It raises a profound philosophical question about necessity. Do mathematical truths like 2 + 2 = 4 exist in some eternal, Platonic sense, regardless of whether a universe exists to exemplify them. And if they do they constrain what kinds of physical universes can possibly come into being? In this view, our cosmos is not free to have any arbitrary set of laws. It can only instantiate those mathematical structures that are logically permissible under the axiomatic rules. This makes the order we see not a fortunate accident, but a logical inevitability. The breathtaking symmetry of a snowflake and the elliptical orbit of a planet are both expressions of a deeper, immaterial architecture of thought, where the source of all cosmic harmony is nothing more and nothing less than the irrefutable consistency of logic itself. The idea that logic alone could dictate cosmic structure feels almost serene, but our next theory finds profound order in a concept most of us associate with decay. Entropy is often described as the universe's slide into disorder, a measure of chaos. Yet a deeper principle, that of maximum entropy production, suggests something far more creative. It proposes that systems, when pushed away from equilibrium, don't just passively settle. They actively evolve along the paths that dissipate energy and produce entropy the fastest. This drive is not toward bland uniformity, but can forge stunning complexity. Picture a river carving a canyon. The water is simply following the path of least resistance, seeking the lowest gravitational energy state. But in doing so, it doesn't create a smooth, featureless channel. It sculpts intricate networks of tributaries, waterfalls, and oxbow lakes, a breathtakingly ordered structure that emerges from the relentless process of energy dissipation. This principle scales up to cosmic proportions. The vast, swirling arms of a spiral galaxy, the intricate web of filaments connecting galaxy clusters, even the complex chemistry on a warm, wet planet, all of these can be seen as natural outcomes of a universe seeking to maximize the flow of energy and the production of entropy over immense spans of time and space. In this view, cosmic order is not imposed from outside or written in a primordial code. It is an emergent property, a pattern that naturally arises because it is the most efficient way for energy to move and spread. Life itself, with its exquisite complexity and relentless metabolism, might be the ultimate expression of this principle on a planetary scale, a highly ordered system that exists precisely to accelerate the flow of energy and increase entropy in its environment. This theory beautifully reframes the relationship between chaos and organization. They are not opposing forces, but partners in a grand thermodynamic dance. The structured galaxies and living cells we see are not exceptions to a rule of disorder. They are the direct and inevitable consequences of that very rule playing out across the cosmos. Order emerges not in spite of the universe's tendency toward entropy, but because of it. But if logic provides the rules, where do the breathtakingly beautiful patterns come from? Roger Penrose, a physicist who has shaped our understanding of black holes and cosmology, points us back to an ancient idea with a modern twist. He champions a view where certain mathematical forms possess an objective reality, a kind of Platonic realism in physics. For Penrose, the universe is not just described by mathematics, it is compelled by it. He points to objects like the Mandelbrot set, that infinitely complex, infinitely beautiful fractal shape generated by a simple equation. This form was not invented, it was discovered, a truth that existed in a mathematical realm long before any human mind conceived of it. In this perspective, cosmic order is the physical manifestation of these timeless, perfect ideals. The spiral arms of a galaxy, the arrangement of petals on a flower, or the crystalline structure of a snowflake are not accidents of physics. They are echoes of a deeper geometric truth, forcing their way into our material reality. This blends Plato's 2,000-year-old philosophy with the cutting edge of science, suggesting that when a physicist like Einstein uncovers a beautiful equation describing gravity, he is not creating a model. He is having a revelation, brushing against a pre-existing truth that the universe itself is obligated to follow. It explains why nature so often resolves into elegance, why the most fundamental laws we find are expressed not in messy, arbitrary numbers, but in clean, symmetrical equations. The order we seek is not emergent from chaos, but imprinted from a realm of pure form, a cosmic blueprint written in the language of geometry long before the first star ignited. Darwin's theory of evolution reshaped our understanding of life on Earth, but could its principles operate on a cosmic scale? This is the audacious proposal of physicist Lee Smolin, who asks us to consider a universe that is not a static creation, but a living, reproducing entity. In his theory of cosmic natural selection, the cosmos itself is subject to evolutionary pressures. The mechanism for this grand reproduction is as dramatic as it gets: the black hole. Smolin suggests that inside the singularity of a black hole, where our known laws of physics break down, conditions might be ripe for the birth of an entirely new universe. This daughter universe would not be an identical copy. Just as genetic mutations introduce variation in biology, the physical laws of this new cosmos might be slightly tweaked, a random, quantum change in a fundamental constant. This sets the stage for a breathtaking form of cosmic evolution across a multiverse of lineages, universes that, by chance, have laws conducive to forming many stars and, crucially, many black holes become the most prolific reproducers. They spawn more offspring universes, passing on their law sets. Universes with laws that prevent black hole formation become evolutionary dead ends. Over countless generations, the population of universes in the multiverse would become dominated by those with physics fine-tuned for black hole production. Our own universe, then, with its abundance of stars that collapse into these gravitational behemoths, would not be fine-tuned for life by a designer. It would be fine-tuned for fecundity by a blind, evolutionary process. We, and all the complexity we see, are simply byproducts of a cosmos that is exceptionally good at making more of itself. This theory introduces a dynamic, almost biological narrative to cosmology. Cosmic order is not a frozen, perfect set of rules. It is a temporary winning formula in an endless competition across eternity, where the ultimate measure of fitness is not survival, but prolific cosmic childbirth. This idea of a universe born from nothing is not just a metaphor, but a precise physical proposal. The zero-energy universe hypothesis offers a stunningly elegant answer to the most basic question of all: why is there something rather than nothing? The key insight is that the something we see might be perfectly balanced by an invisible negative something. All the mass and energy contained in every star, planet, and galaxy represents a vast amount of positive energy. But gravity, according to Einstein's theory, possesses a kind of negative energy, a binding force that holds the cosmos together. In a closed universe, these two quantities could cancel each other out exactly, summing to a net energy of zero. If that's true, then our entire magnificent universe is, in the most fundamental bookkeeping sense, nothing at all. This opens a breathtaking possibility for its origin. In the quantum realm, empty space is never truly empty. It is a seething foam of virtual particles that pop into and out of existence on borrowed energy, fleeting quantum fluctuations allowed by Heisenberg's uncertainty principle. In a state of true nothingness, a primordial void with zero total energy, a particularly large and persistent quantum fluctuation could have occurred. Because the total energy was zero to begin with, this fluctuation would not violate any conservation laws. It could simply be a random bubble of space-time and matter appearing from the void, its positive energy perfectly offset by the negative gravitational energy of its own expansion. In this view, the Big Bang was not an explosion in a pre-existing void, but the sudden, spontaneous appearance of the void's opposite, a structured universe born from a momentary hiccup in nothingness. The cosmic order we then see, the galaxies and laws, would be the stable configuration this particular fluctuation happened to settle into, a fortunate and statistically rare accident frozen into permanence. This concept profoundly reframes our existence. It suggests that everything we know and are emerged not from a divine command or a necessary mathematical truth, but from the same unpredictable quantum jitter that creates virtual particles in a lab. Our quest for a source of cosmic order leads us to a conclusion that is both humbling and awe-inspiring. The grand architecture of reality may be the most beautiful and complex accident possible, a shimmering pattern written on a canvas of absolute zero. Stephen Hawking once asked what happened before the Big Bang, and his answer was that the question itself might be meaningless. Along with physicist James Hartle, he proposed a vision of cosmic origins so elegant it redefines our idea of a beginning. This is the no-boundary proposal. Imagine, if you can, the entire history of our universe not as a line starting at a point, but as a sphere like the surface of the Earth. On our planet, you can travel north forever, and eventually you will reach the North Pole. But the North Pole is not an edge, not a boundary where the Earth stops. It is simply a point where the concept of going further north loses meaning. Hawking and Hartle suggested the universe is similar in 4 dimensions. The Big Bang is not a fiery explosion from nothing, but more like the North Pole of space and time, a point where the universe is extremely small and hot, but not a true beginning from nothing. In this model, the cosmos has no initial boundary, no sharp edge where time starts. It is a smooth, self-contained geometry, finite in extent but without any boundary, just as the surface of a sphere is finite but has no edge. This has a profound implication for cosmic order. The laws of physics do not need to be imposed at a singular starting gun. Instead, they emerge naturally and inevitably from the smooth, no-boundary geometry itself. The order we see, from the uniformity of the cosmic background radiation to the very arrow of time, is baked into the shape of reality from the start, not as a set of rules written on a blank slate, but as the intrinsic properties of a universe that simply is. It provides a mathematically coherent picture where the universe needs no external creator or prior cause, because in this framework, asking what came before is like asking what is north of the North Pole. The cosmos in its entirety is its own complete and orderly explanation. The smooth, mathematical necessity of the no-boundary proposal offers a universe complete in itself. But what if cosmic order is not a frozen geometry or a logical necessity, but something that grows and learns? Biologist Rupert Sheldrake presents a theory that is as controversial as it is fascinating: morphic resonance and collective memory. In this view, the natural world is not governed solely by fixed, immutable laws. Instead, Sheldrake proposes the existence of morphic fields, invisible organizing patterns that shape everything from the growth of an oak tree, from an acorn to the instinctive behavior of a flock of birds. These fields are not static, they are built up and strengthened by repetition. The more often a particular pattern occurs, the more probable it becomes for that pattern to happen again, anywhere in the universe. This is the resonance, a kind of cumulative memory that influences future events. Apply this to the cosmos itself, and you get a radical reimagining of cosmic order. The laws of physics, the very symmetries we hold as fundamental, might not have been set in stone at the moment of the Big Bang. They could be cosmic habits, patterns that have grown increasingly stable and probable over billions of years of universal repetition. The first time a star formed, the process might have been tentative, exploring possibilities. But as trillions of stars formed in the same way, that specific pathway of gravitational collapse and nuclear fusion became ingrained, resonant, and vastly more likely to occur again. In this framework, the universe is not a machine running on a pre-written program. It is more like a living system with a memory, evolving its own structure through experience. The breathtaking order we see in spiral galaxies or planetary orbits is not a decree, but a deeply ingrained custom, a rhythm that the cosmos has settled into through practice. This theory deliberately blurs the line between biology and cosmology, introducing a non-materialistic, almost psychological mechanism for how patterns solidify across space and time. While mainstream science largely rejects morphic fields due to a lack of conventional evidence, the idea's power lies in its narrative. It suggests a cosmos that is not cold and deterministic, but one that accumulates experience, where order is not imposed but cultivated, a story written not in equations, but in the persistent echoes of everything that has ever happened. The idea of a universe with a memory suggests a cosmos that learns from its own past. But what if its entire history is just one collision in an endless, higher dimensional dance? String theory, that ambitious quest for a theory of everything, opens a door to a reality far stranger than a single, isolated universe. Within its framework, our entire cosmos might be just a three-dimensional membrane or brane, floating within a vast, higher-dimensional space called the bulk. In this breathtaking model, cosmic order finds its origin not in a singular explosion from nothing, but in a monumental encounter. The Ekpyrotic and Brane collision theories propose that our Big Bang was the result of our brain colliding with another parallel brain drifting through the bulk. This titanic impact would have released an immense amount of energy, flooding our brain with the hot, dense plasma that became the seeds of all matter and structure. The very laws of physics we experience, the strength of forces and the masses of particles, would not be fundamental truths of an isolated universe. They would be set by the specific properties of our brain, its tension and vibrational modes, and the precise details of that ancient collision. Think of it like two sheets of paper floating in a gentle breeze representing the brains. When they brush against each other, the contact creates a ripple of heat and motion across their surfaces. That ripple, from our perspective trapped on one sheet, is the entire history of our expanding universe. This transforms the Big Bang from a beginning into an event, a phase in a much larger cycle. This leads to the Ekpyrotic or Cyclic scenario. After a collision, the brains move apart, each carrying a new, hot universe on its surface. That universe expands and cools, stars form and die, and eventually it becomes cold, dark, and empty. But gravity, or perhaps a hidden force in the bulk, slowly draws the brains back together over trillions of years until they collide once more, igniting a new cosmic cycle from the ashes of the old. In this eternal rhythm, cosmic order is not created once and for all. It is reset and potentially refined with each collision. Subtle changes in the approach or angle of impact could tweak the universal constants in the newborn cosmos, introducing a form of cosmic evolution across cycles. The breathtaking mathematical harmony we spend our lives studying might be the local physics of one particular brain, a shadow cast by the true, hidden geometry of the higher dimensional bulk. This theory profoundly expands our dimensional thinking. It implies that the source of all law and structure lies outside our perceptual reach, in realms we can describe with equations but never directly experience. Our quest to understand cosmic order becomes an act of cosmic cartography, trying to map the contours of an unseen landscape by studying the peculiarities of the world it projects. Amidst these grand collisions and cosmic cycles, there is a quieter, more pervasive kind of order at work. It is the silent, guiding hand behind every arcing baseball, every bending beam of starlight, and every planet tracing its ellipse around the sun. This is the principle of least action, a cornerstone of physics that feels less like a law and more like a cosmic preference for efficiency. At its heart, action is a specific mathematical blend of energy and time. The principle states that any object moving through space, from a tiny photon to a massive galaxy, will follow the one path out of all possible paths that requires the least amount of this quantity. It is as if the universe is a master economist, always selecting the most budget-friendly route through space-time. A beam of light refracting through water doesn't just obey Snell's law. It calculates in an instant the fastest path from point A to point B. A planet orbiting a star isn't just pulled by gravity. It settles into the one trajectory that perfectly balances its kinetic and potential energy over its entire journey. This principle unifies phenomena that seem utterly unrelated, revealing a stunning underlying economy. The chaotic dance of colliding particles and the majestic sweep of celestial mechanics are both governed by this single, elegant rule of thrift. This introduces a fascinating, almost philosophical dimension. The universe appears to have a goal, a telos, to minimize action. It isn't just stumbling forward, it is optimizing, making choices that lead to the most economical outcome. Some see in this a profound mathematical elegance, a hint that the cosmos is not just orderly, but optimally so, shaped by a logic of supreme efficiency. The structure we see, from the parabolic arc of a thrown ball to the complex orbits within a solar system, emerges not from a list of separate force laws, but from this one fundamental tendency of nature to take the path of least resistance through the fabric of reality. It suggests that cosmic order might be, at its core, a form of cosmic bookkeeping, where every motion is an entry in a ledger balanced to perfection. But if the universe is on a relentless path toward efficiency, where does that path ultimately lead? Frank Tipler's omega point theory offers a vision of cosmic destiny so grand it merges physics with eschatology. He proposed that the universe's story does not end in a cold, silent fade, but in a fiery, transformative convergence. Imagine a cosmos that, after its long expansion, begins to contract under its own gravity, heading toward a final big crunch. As all matter and energy are compressed into an ever-shrinking volume, the temperature and density soar toward infinity. In this extreme environment, Tipler saw not just an end, but a beginning of a different kind. He argued that as the universe collapses, the potential for information processing becomes infinite. Intelligent civilizations, perhaps having evolved into vast, distributed forms of consciousness, would harness this escalating energy to perform computations on a scale we cannot fathom. Their collective knowledge and awareness would expand exponentially, approaching a singularity of mind as the physical universe approaches its spatial singularity. This ultimate moment, the omega point, represents the culmination of all possible knowledge, experience, and order. In this view, cosmic order is not merely a set of starting conditions or emergent habits. It is teleological, purposefully driving toward an end state of perfect complexity and unified consciousness. The entire history of the cosmos, from the first stars to the rise of civilizations, becomes a necessary prelude to this final, transcendent act of understanding. While highly speculative and resting on specific cosmological models that may not align with our current understanding of an ever-expanding universe, the omega point theory is powerful for its narrative ambition. It combines hard physics with almost theological themes of destiny and resurrection, suggesting that the universe is not just a place where order happens, but a process that learns, remembers, and strives toward an ultimate state of knowing itself. It reframes our existence as steps on a path toward an apocalyptic enlightenment, where the source of cosmic law finds its final expression in a moment of infinite thought. Our universe is built on a lopsided foundation, a fundamental imbalance written into the first moments of existence. For every particle of matter, physics tells us there should be an equal and opposite particle of antimatter, a perfect mirror that annihilates on contact with its twin. If the Big Bang had produced a perfectly symmetrical soup of both, all particles would have met their counterparts, resulting in a universe filled with nothing but light, a vast, empty glow. Yet here we are in a cosmos teeming with galaxies, stars, and planets made of matter. This profound asymmetry, the mystery of why matter dominates, is not a minor detail. It is the essential precondition for all cosmic structure. Without it, there would be no stuff to clump into anything, no raw material for gravity to sculpt. The order we see hinges entirely on this ancient, inexplicable bias. The leading theories point to subtle cracks in the early universe's perfect symmetry, processes with names like charge parity violation or CP violation for short. In the unimaginable heat of the first second, certain particle interactions, perhaps involving elusive neutrinos, behaved very slightly differently than their antimatter mirror reactions. For every 10 billion matter-antimatter annihilations, a single particle of matter survived by chance. That 1 in 10 billion remnant is everything. All the galaxies, every atom in your body, is made from that tiny surplus, the ash left over after the Great Annihilation. This reveals a breathtaking connection between the smallest scales and the largest structures. The specific oscillations of a nearly massless neutrino in the first fraction of a second set the stage for the grand architecture of galaxy clusters billions of years later. Cosmic order, then, emerges not just from gravity and expansion, but from a razor-thin margin of victory in a primordial war between matter and its shadow. It shows us that the universe's habitability was not guaranteed, but won by the slimmest of chances, a microscopic bias frozen into the fabric of reality that made all future complexity possible. This razor-thin margin of matter over antimatter gave the universe its substance, but what is the shape of that substance? The 29th theory suggests a breathtaking answer, one that finds harmony not in unique laws for each scale, but in a single, endlessly repeating pattern. This is the idea of a fractal cosmology. In this vision, the universe is not neatly divided into a quantum realm with one set of rules and a cosmic realm with another. Instead, it possesses a scale-invariant, self-similar structure where the same intricate patterns appear again and again, no matter how far you zoom in or out. Think of a coastline seen from space, its rugged outline. As you descend, you see bays and peninsulas, then individual rocks, then grains of sand, each level revealing a similar complexity and jagged shape. Fractal cosmology proposes that the cosmos itself is built this way. The clustering of galaxies in a vast supercluster might mirror, in its statistical distribution, the way matter clumped in the early universe, or even the way energy fluctuates at the quantum scale. There is no fundamental bottom level, just an endless recursion of order, each layer a reflection of the one above and below. Researchers like Laurent Nautel have explored this through the lens of scale relativity, suggesting that the laws of physics themselves might transform smoothly from one scale to another, governed by fractal geometry rather than by a fixed set of traditional equations. This offers a visually stunning vision of cosmic order. The universe becomes an infinite mosaic, a cosmic kaleidoscope where the spiral of a distant galaxy, the swirling of a hurricane, and the pattern of branching in a tree all whisper the same geometric secret. It implies a deep and elegant simplicity, a universe that builds its immense complexity not from thousands of different rules, but from one beautiful, recursive principle played out across an unimaginable range of sizes. In such a cosmos, to understand the very small is to catch a glimpse of the very large, and the source of all law may be nothing more than a single, perfect shape, echoing itself into eternity. The final theory returns us to the most intimate mystery of all, the nature of our own awareness. Panpsychism offers a radical proposition that consciousness is not an accidental byproduct of complex brains, but a fundamental feature of reality itself, as basic as mass or charge. In this view, a flicker of subjective experience, however simple, might be present in every particle, every field, and every star. The cosmic order we have spent this entire journey tracing, from mathematical structures to emergent laws, would then be deeply intertwined with a universal, though not necessarily unified, consciousness. Physical laws might not just be cold equations. They could be the observable habits of a cosmos that is, in some profound sense, awake and experiencing itself from the inside out. This addresses what philosophers call the hard problem of consciousness, the puzzle of how subjective feeling arises from objective matter. Panpsychism suggests it never had to arise because it was always there, a property woven into the fabric of existence from the first moment. The breathtaking mathematical harmony we find, the elegant principles of least action and symmetry, might be reflections of a cosmic mind's inherent tendencies toward coherence and pattern. It is a theory that beautifully bridges epochs, connecting the animistic intuitions of our earliest ancestors, who saw spirit in river and stone, with the deepest questions of modern physics and philosophy. It asks us to consider that order and awareness are not separate phenomena, but two facets of the same diamond, different ways of perceiving a reality that is both rationally structured and intrinsically experiential. This idea brings our exploration full circle, from divine architects and mathematical forms to self-organizing systems and participatory observation, ending with a universe that is not just known, but in some way knows itself. It leaves us with a final, humbling reflection that in our quest to understand the source of cosmic order, we may have been uncovering the contours of our own deepest connection to everything that is. This journey through 30 possibilities reveals a stunning landscape of human thought. We have moved from divine architects and mathematical forms to self-organizing systems and cosmic evolution, from the silent geometry of spacetime to the hum of a universal consciousness. Each theory, in its own language, answers the same profound call: why is the cosmos not chaos? Some, like cosmic inflation or symmetry breaking, ground order in physical processes, events frozen into law during the universe's fiery birth. Others, like the mathematical universe or Plato's forms, see physical law as a shadow cast by deeper, timeless truths. Theories of emergence, from thermodynamics to fractal cosmology, find order bubbling up from below, a natural consequence of simple rules playing out on a grand stage. And still others, from the participatory Anthropic principle to Panpsychism, weave our own awareness into the fabric of reality itself, suggesting the observer is part of the equation. This breathtaking diversity is not a sign of confusion. It is a testament to the depth of the mystery we are confronting. No single perspective, whether from a telescope, a philosophy text, or a meditation, seems capable of capturing the whole picture. The quest for cosmic order is not a race with one winner. It is more like a symphony where each theory plays a distinct movement, exploring a different dimension of the same eternal question. By placing them side by side, we begin to see the contours of something larger. Perhaps cosmic order is not a singular source to be found, but a multifaceted phenomenon to be appreciated. The elegant efficiency of least action, the creative drive of maximum entropy, the resonant habits of morphic fields, and the logical necessity of mathematical axioms, these are not necessarily competing truths. They could be different lenses, each revealing a genuine aspect of a reality too complex for any one story. This synthesis invites a humble and expansive view. Our universe might be a tapestry woven from threads of physics, logic, biology, and mind. A grand synthesis where the mechanical and the meaningful are not opposites, but partners in a single, magnificent unfolding. The true source of cosmic order may be the interplay of all these principles, a harmony we are only beginning to hear. This rich tapestry of ideas leaves us not with a single answer, but with a deeper, more resonant question. The origins of cosmic order remain one of humanity's greatest enigmas, a profound mystery that forever blends the sharp tools of empirical science with the timeless wonder of philosophical inquiry. We have journeyed from divine blueprints to quantum fluctuations, from the silent logic of mathematics to the hum of a conscious cosmos. Each theory, in its own way, challenges us to think bigger, to question our most fundamental assumptions about what reality is and why it behaves with such breathtaking consistency. This journey underscores a beautiful truth about our species. The search for order is itself a powerful testament to our innate curiosity and our unyielding drive to make sense of the vast, silent cosmos we call home. It is a quest that defines us, connecting the ancient astronomer charting the stars on a clay tablet to the modern physicist parsing data from a space telescope. If any of these 30 mind-expanding ideas sparked your imagination, we would love to hear from you. Share your favorite theory or the one that puzzles you most in the comments below. For more journeys to the edge of understanding, subscribe and join us as we continue to explore the deepest mysteries of space and existence. And always keep looking up. The final chapters of this story are not yet written, and the answers we seek may still be waiting, inscribed in the silent, shining language of the stars.